conducting cavities, which he will elaborate on. I request Professor Vijay Raghavan to introduce the speaker before we start the lecture. Thank you.
Thank you, Parag, for hosting Tanay for this asset colloquium. So, as some of you may already know, Tanay was a PhD student here at the IFR. In fact, he was the first student in my lab and helped set up the lab from scratch. Lots of fun memories. And so, thank you. The lab exists today because of the efforts you did almost now 12 years ago. Tanay is now an associate scientist at the Superconducting Materials and Systems Center at Fermilab, where he serves as the deputy head of the 3D Quantum Systems Department. He leads the effort to develop the next generation 3D quantum computing architectures based on superconducting radio frequency cavities, with the goal of building a prototype quantum processor that achieves dramatically improved coherence times and enhanced controllability. So before Fermilab, he was a postdoctoral researcher at the University of Chicago under Professor David Schuster, and he worked on things like autonomous quantum error correction, quantum search algorithms, and demonstrated a qudit-based quantum processor. So as he will explain, this approach to quantum computing is connected but different than the approach we work here at TIFR and also being done in big labs like IBM and Google, where the fundamental storage unit where the quantum states are stored are different. And then I will show that that has some advantages over the conventional methods, and he will hopefully convince us that this is one practical way of building a quantum processor. So thank you, Tanay. Welcome to TIFR again, and over to you.
Thank you, Vijay, for the nice introduction, and Parag for hosting this colloquia. As Vijay mentioned that I was a PhD student here, and I have very nice memories of this specific room, of taking lectures, listening to other fantastic colloquia, and also giving talks. So I'm super delighted to visit TIFR after, I think, about 5 years and giving this talk. All right, so let's get started. Before I start, I would like to slightly introduce our center, SQMS, which you may not know about. So back in 2020, the Department of Energy in the USA established 5 national quantum centers. It's called SQMS, QNext, QSC, C2QA, and Quantum System QSA. SQMS, all of them are led by one of the national labs with many partners, including academia and industry and other national labs. SQMS, which stands for Superconducting Quantum Materials and Systems Center, has currently 36 partner institutes worldwide and more than 550 collaborators. The goal is that we want to bring the power of industry, academia, and national labs to bring transformational advancements in the development and deployment of high coherence superconducting quantum systems. This includes various aspects of quantum computing, starting from reducing qubit losses, looking at the very fundamental level of materials, and using that, we try to build high coherence quantum systems, specifically using 3-dimensional cavities. And we are also working towards developing efficient cryogenics to build scaled up quantum systems and eventually use all these for quantum computing, simulation, and sensing. All right, with that introduction, here is my outline. I'll talk about the development of bosonic or cavity-based quantum processing units and tell you what are the advantages of such systems. And then I'll discuss what are the strategies to further improvement of this kind of systems that can help in actually solving practical problems. So as a starter, I'll just give you a quick introduction to the qubits. So what are the basic requirements for a quantum computer? You need to have at least a quantum 2-level system, which is known as a qubit. It's labeled with 0 and 1. You should be able to create arbitrary superposition states. Then you should be able to measure the state of the qubit accurately. And you should be able to couple multiple qubits because you need to scale up the system to increase the power of the computer. And it should have a scalable architecture. So there are many ways, different platforms to build a qubit. For example, trapped ion systems, superconducting circuits, photonic crystals, nitrogen vacancy centers, NMR, neutral atoms, and quantum dots. Among all of them, the superconducting circuit is quite special. You see all of them use kind of fundamental blocks like atoms or ions or photons, so which are microscopic, whereas superconducting circuits are quite macroscopic. You can even see them with bare eyes. The dimension of this chip is about 7 by 7 millimeter. And even though they are macroscopic, they show quantum properties. And this brings to the topic of this year's Physics Nobel Prize, where John Clark, Michel Devoret, and John Martinez were awarded the Nobel Prize for the discovery of macroscopic quantum mechanical tunneling and quantization in an electrical circuit. So I'd like to mention that Michel Devoret is the advisor of Vijay. So that makes me an academic grandchild of a Nobel laureate. I'm very glad about it. So if you like to read about the more scientific background, you can check this QR code and go through the details. But their work, which is basically showing that macroscopic objects can also show quantum tunneling, is why we can actually build this kind of superconducting qubits today. And I'll explain one type of superconducting qubit, which is known as the transmon. This is very popular and widely used among academia and industry. So we can begin with a harmonic oscillator, which has parabolic potential with equally spaced energy eigenstates. So if you start from the ground state and drive it on resonance, it is not going to stop at 1. It will keep climbing because all of the states are equally spaced. So it's difficult to control this kind of harmonic oscillator. On the other hand, if you can make the harmonic oscillator anharmonic by having some nonlinear element, then you can have anharmonic, like in this case, a cosinusoidal potential with unequally spaced energy eigenstates. And then because the transitions are unequal, if you start from the ground state and apply an on-resonance drive, the excitation will continue to stay within the 0 and 1 subspace. That is how you can isolate the rest of the energy levels from the bottom two, which act like a qubit, which we just represent as 0 and 1. This can be achieved with this kind of circuit, which looks like the LC oscillator, but the linear inductor here is replaced with a nonlinear inductor, which can be built using something called a Josephson junction, which is a thin insulating layer sandwiched between two superconductors. Here is a picture of a transmon device where this capacitor is formed by these two pads, metallic pads, and at the center we have a junction. Actually, in this case, we have two junctions which form a squared loop. So this is the main or common element which is used across the industry. For example, like IBM, Rigetti, Google, and USTC China, they build 2D superconducting processors using the transmon. This is called 2D because all these circuits are made on chip by drawing electrical circuits. This one is from Vijay's lab, where I was also working with this device for measurements, and this is called Trimon. And it is actually India's first superconducting 3-qubit processor. Now, this kind of 2D circuits has some limitations. And we like to actually look at other ways of building superconducting platforms. For example, 3D superconducting devices. So in this case, there are also many options. For example, we can use something called a stub cavity or flute cavity or some elliptical shaped cavity or mushroom cavities. Okay, I'll explain in more details later. There are other type of superconducting platforms as well, again from Vijay's lab. So these are called ring resonators. At the edge of these are the transmons connected by a ring cavity, and this is from IBM with connected by bus resonators. But here, the information is stored in these 2D devices, the transmons, which are 2D. What we want to do is store the information in the 3D cavities. So this can be thought as hybrid 2D, 3D, or just semi-3D cavity systems. So in our case, we want to actually change the scenario. So normally this anharmonic oscillator, which is a transmon, is used as a qubit to store the quantum information, but we want to store the quantum information in the harmonic oscillator. The reason is that in harmonic oscillator, you can control many levels, d larger than 2, and one of the main advantages is that they can have much, much longer coherence. I'm going to show you details of those. And in that case, the transmon will be used as an ancilla component to prepare this kind of quantum states. So what are the benefits of using harmonic oscillators? So first of all, they can have much longer coherence, which means we can perform more operations and can have accurate results. And then we can have much larger Hilbert space because we are having like D levels. And that enables qudit encoding. So it's called quantum d-dimensional system, that's known as qudit. That because we have qudits, we need to have much less cables. And that results in much less heat load in the fridge in which they are placed. And also you need less room temperature control in electronics. And finally, with certain geometry, we can have all-to-all connectivity that will result in a scaling as t to the power n instead of 2 to the power n for a qubit. All right, so since we are going to use 3D cavities, so first we have to understand or decide what kind of geometry is best, okay? Now there are many ways you can build a 3D cavity. The simplest one is called pillbox or rectangular cavity. Then you can have cylindrical cavity, stub or post cavity. Then this is seamless fluid cavity, and some of them are elliptical shaped. So to understand which one is the best, you can understand it quite intuitively. So the question is, which one should have the least amount of loss, okay? So the cavity is just an enclosure within which you have the electromagnetic field, right? So if you operate that under vacuum, you can see that the vacuum is lossless. It cannot absorb any energy. The major source of loss is the surface of the cavity, okay? So then the question is, what kind of geometry minimizes the surface to volume ratio, okay? So we need to find a geometry where we have the maximum volume and minimum amount of surface. Any guess? It might have, which is kidding. So yeah, so you might have guessed it that it's the sphere. Sphere has the minimum ratio of surface to volume, okay? So if you, from the geometrical point of view, spherical cavity would be the best, but they are difficult to operate because of this complex structure of the eigenmodes. So we use something closer to the spherical geometry, which is the elliptical geometry. It's more practical. So,
well, you say it's more practical because of the spacing of the eigenmodes?
Not because of the
construction.
Because of the electromagnetic field structure within the sphere. How you probe it and how the ancilla component goes inside the spherical cavity. It makes the elliptical geometry much easier to do. And Fermilab has been building this elliptical cavity. By the way, you can stop me anytime and ask questions. Fermilab has been building these elliptical cavities mainly for particle accelerators. So this is one such cavity. This is called 9-cell Tesla cavity. So just let me tell you the nomenclature about this. So each of these donut shapes are called cell. These sections with the largest diameter is called the equator, and the small diameter sections are called the iris. This section is called the beam pipe, the central column, because particles are sent through this beam pipe. And these are the RF ports through which energy is introduced in the cavity. So the Tesla name is not related with Nikola Tesla or a company you might be familiar with. It stands for tera-electron volt energy superconducting linear accelerator. So these cavities are made of pure niobium, generally around 1.3 gigahertz cavity. And most importantly, they can reach a quality factor of 10 to the power 10, still in billion. So these are actually the world's best cavities we can make, okay? So the question is, because these cavities are so nice, can we use them for quantum applications? So these numbers are obtained actually with much higher power because particle accelerators require a large power to accelerate the particles. And usually these operate around 1.5 Kelvin. But for quantum applications, we need to go down to very low photon numbers, usually around single photon level. And we need to also operate at millikelvin. So we have to test whether these cavities are good for around those parameters. So we did test that. So we measured 3 Tesla cavities around these frequencies. What I'm plotting here is the quality factor as a function of temperature. So don't need to focus on all these curves. Let's look at the green one and the orange one here, okay? So, and this data is taken around single photon level. So you can see that even at millikelvin, this is around 20 millikelvin, the quality factor is larger than 10 to the power 10. And if you convert that quality factor into photon lifetime using this expression, Q equals omega times T1, then you can see here the lifetime is larger than 1 second, right? It's an extremely high coherence numbers. So this is the motivation why we want to use this kind of cavities for quantum computing. So we want to continue with this Tesla style cavities. And let's see, so these Tesla style cavities can be considered as harmonic oscillators, like LC oscillator here. And they have harmonic potential and equally spaced energy eigenstates, as I showed earlier. So usually when you cool it down to 20 millikelvin, you start from the ground state. So it's the vacuum state. And you can excite to the first excited state, which if you use only these 2 levels, then it will be called as a qubit. If you use 3 levels, it would be called qutrit, 4 levels is qquart, and so on. You can climb the ladder. Usually we call it a qudit, which stands for quantum D-level systems. But as I mentioned earlier, that these are just simple linear oscillators. You cannot create, these are quantum states. You cannot create these quantum states just by driving these cavities. You need to have some sort of nonlinear ancillary component inside these cavities. So for that, we use the same transmon chip, okay? As I showed you, transmon is just an harmonic oscillator, and usually we use the bottom 2 or 3 levels as for these purposes. So how do we incorporate this transmon into the Tesla cavities? This is our version 1, our first attempt in doing this. What I do, we take a transmon, fabricate it on top of silicon or sapphire chip in this long rod, and insert it inside the Tesla cavity so that it comes almost to the center of it. Then it can interact with the electromagnetic cavity. Here I'm showing you the electric field of the transmon, and then the electric field of the TM101 mode, which is the fundamental mode of this cavity. It's TM, not TE. Yeah, so transverse magnetic. Coupling is still electric. It's just the nomenclature, like how the electric field is oriented. It still couples to the electric dipole moment. So to test that they are interacting, what we do, we perform qubit spectroscopy with coherent states. So coherent states are simple classical states. So if you drive the cavity with certain power, the state that will be created inside the cavity are called coherent states. So on the y-axis, we are driving the cavity with increasing power. On the x-axis, we are probing the qubit or the transmon with different frequencies. When we don't drive it, we know that the cavity is dominantly in the ground state, and this signal feature corresponds to 0 photon. Then if you increase more power, you start to populate the 1 photon and 2 photons and so on. So this is telling us that the qubit can actually sense the number of photons inside the cavity, or we have achieved photon counting. This is done with coherent state, so which is kind of classical, but we want to test that whether you can create quantum states. So we did prepare quantum state, in particular, the first excitation state. By the way, yes. So the question is, why are the frequencies different? It's a very good question. So we make the coupling between the transmon and the cavity strong enough so that the frequency of the transmon shifts by some unit when we introduce 1 photon in the cavity. It's called the dispersive shift. So if I put 1 photon, let's call it chi, the frequency of the qubit will be shifted by chi. If I have 2 photons in the cavity, it will be shifted by 2 chi. I'll show you just the data later on. So that's why it's shifting to the left. And the value of the chi is negative, that's why it's shifting to the left.
How are we measuring the qubit frequency? There's another cavity?
Very good question. How are probing the transmon qubit here? So actually this is 3D cavity and it has many modes like any other cavity. So in this particular case, we are using another cavity mode to measure the state of the qubit. So there are many modes which actually interact with the cavity, with the transmon apart from the fundamental mode. So we use another mode to measure the qubit. Here the storage cavity. So right, so this is 5 gigahertz. The other mode was around 7.8. Yeah, the reason being that mode has actually, so I didn't mention, so that their antennas are entering from the edge, like here or here, and that mode has significant participation around the antenna. The fundamental mode doesn't have, because otherwise it will be too lossy. And this turns out to be not a good idea. I'll show you later like how we improved it. Right, so we prepared so this is called the Fock states, the Fock 1, 2, 3, and so on. So we prepared the Fock state 1, and this is a representation of the Fock state using Wigner tomography for the verification. Then we measured the lifetime of this Fock state. That is what is very important. So we found that to be about 3 milliseconds. So again, remember the transmons coherence are very small, much smaller, like around 100 microsecond, and this coherence is 3 millisecond, okay? So like 30 times better. Now, why is it 1 second? Very good question. So 1 second, remember, was, I didn't actually explain that, why. The 1 second was done after doing a lot of treatment. So after preparing the cavity, I will explain what are the treatments were. Once you do all those treatment and you have to keep it under vacuum, then you can go to 1 second. In this first version, we didn't do all this complication. We just wanted to see what is the performance for the bare cavity.
So, because I was thinking that because of the introduction of all that rod and the chip, that will probably also affect.
Exactly. So that is why I had to. So in this case, the chip itself is quite lossy, and that introduces a lot of loss. I'll show you the data.
What's the material of that comp?
So this is sapphire. So the T1 was about 3 milliseconds, the T5 was about 2 milliseconds, still higher than transmon, but not as good. So we can actually climb the ladder in this case as well. So starting from 0, here I'm showing the spectroscopic data. So this peak of the qubit shows, tells us that we have 0 photon or no photon in the cavity. When you have 1 photon, the peak shifts to the left, 2 photons further left, and then 3 photons. So all of them are separated by this dispersive shift or the chi shift. And this is the signature that we have actually climbed the ladder. For the experts, so we can keep climbing this ladder. For the experts, this is done with what is called snap-on displacement, and I'll not explain what that is for now. Okay, so even though we did this was the first version, it had many flaws. So first of all, like Vijay asked, why not 1 millisecond? 1 second. So when you make just these cavities, pure niobium cavities, and don't do advanced treatments, it shows a lifetime of about 30 milliseconds, okay, between 20 and 30 milliseconds. In this case, it was 30. But after introducing, that is the empty cavity lifetime. If after introducing the qubit chip, it became 3 milliseconds. So quite a lot of reduction. Then there are other problems, like the qubit had higher thermal population, like 8%. This is bad for quantum computing because it's lowering the T2 of the cavity. Then the cavity itself also had a lot of thermal population, like 10%. The readout was very slow, like 16 microsecond and only with 50% readout fidelity, because we are using one higher harmonics of the cavity itself. And then we had another problem, which is qubit readout cross curve. Okay, so we had to improve these numbers. So we made a version 2 where we tried to improve all these numbers. So
Tanay, just one question. High qubit thermal population giving rise to low cavity T2 is just the same inverse effect of what we usually see as measurement-induced dephasing.
exactly.
If you have photons in the cavity, it defaces the qubit. But now if you have photons in the qubit, it
Dephasing
defaces the cavity.
It's the same, yeah, it's the same physics.
Okay.
So in the version 2, this is the result of the version 2, where we can see that we preserved the elliptical geometry more or less. We reduced the beam pipe diameter compared to the previous case. You see the beam pipe was quite large. That is so that the electromagnetic field cannot escape so easily. So in other words, the evanescent field is decays much quickly within the tunnel. Then we retracted the chip. So earlier it was coming all the way to the center, and then we retracted it quite a lot. Then we have made the IDs much larger compared to the standard Tesla geometry, so that the two modes, it creates two normal modes, which we call Alice and Bob after hybridization. And then importantly, we introduced now on-chip readout. So we have the transmon. Earlier we had just the transmon. Now we introduced a readout resonator which is a λ/2 resonator, and also a Purcell filter. This helps in improving the readout of the transmon while having fast control as well. And for the thermal population, we improved the qubit and cavity clamping mechanism using like high purity copper clamping. So with all these things, we improved all the parameters. So in this case, the empty cavity, the Alice mode showed a lifetime of 25 millisecond. And after introducing the qubit, the transmon chip, it went down to only 21 millisecond. Then the thermal population of the qubit was reduced to less than 0.5%. Cavity thermal population was reduced to less than 0.1%. Readout was quite fast, 2 microsecond with 98% fidelity. And the cross curve was much less than 0.1, which helps in reading out the qubit.
So Tanay, can you just go back previous slide? One more.
Like quite back.
No. Keep going forward slowly. I had to. Oh yeah. So no. The Purcell. Acha, now because your Purcell filters actually are inside the beam pipe.
Yes.
Okay. All right.
I forgot to mention, these ports are, so this port is used to drive the qubit because it's closer to the qubit. This port is used to drive the readout, and this is to drive the...
No, I was thinking that if it was the center, how do you, because you're assuming that the coupling of the external field is via the Purcell filter, right? But if you put it in the middle of the cavity, then the cavity field will interact directly with the qubit as well. But here it's, because it's in the beam pipe.
Yeah, so the cavity field almost decays just here, right here. It doesn't reach all the way to the Purcell filter.
Okay.
Not even the readout, actually. The Q of cavity to the readout port was 10 to the power 13 or something. Okay. So let's look at the coherence numbers of this new version 2, which we call a 2-cell system because it has 2 cells. So we had 2 modes. We measured the lifetime. They are about 21 millisecond and 16 millisecond. So this one dropped from 25 to 21. This one dropped from 20 to 16. And the T2 time was larger than 20 millisecond, which translates into T5 of very large number. So we have a very large single photon T1 and T2 in this 2-mode system. And remember, the transmon had a coherence of only 150 microsecond and T2 was 40 microsecond. Despite that, the cavity has much superior properties. Now, as I mentioned, these are harmonic oscillators, so we can climb the ladder. But as you climb the ladder, the T1 drops, and it drops as 1/n. And we experimentally measured that. So this is the 1 photon, and we climb the ladder all the way up to 20 and measure the lifetime of it, and it follows the 1/n dependence. But even then, the 20th Fock state had a lifetime larger than 1 millisecond because we started from more than 20 millisecond. So you can see, so what we have here, 2 high coherence qudits with D larger, like D of 20, okay?
So Tanay, the climbing the ladder is just successive.
I'll explain how we climb the ladder.
Yeah.
So as I mentioned earlier, that we cannot climb the Fock ladder directly because these are linear systems. So if you try to drive, you will create a coherent state, which is a distribution of many Fock levels. So you need to take help of the transmon. So you start with the cavity being in the ground state, 0. And the transmon, I'm labeling them as GEF. Okay, this is a standard nomenclature we use. G for ground, first excited state E, second as F. Again, transmon starts from G. So what we use is called a sideband scheme. I'll show you what it does. So this is the energy eigenstate of the combined joint system. So you can think this as the Fock ladder, like 0, 1, 2, 3. But when the qubit was in the ground state, that's why I'm calling it G0, G1, G2, and G3. We have a similar Fock ladder when the qubit is, the transmon is in the excited state. So E0, E1, E2, E3, and also F0, F1, F2, F3. Of course, it doesn't stop here. There are infinitely many such levels. So we start from the ground in the transmon and the ground in the cavity, which is G0. First, we apply a pi pulse on the transmon, pi GE, which takes the G to the E level. Okay, so from here to here. Then we apply pi EF pulse, which takes from E to F. So we go from here to here, F0. So it's F with 0 in the cavity. And then we apply the sideband pulse, which takes F0 directly to G1. Okay. So after that, what happens, like your cavity jumped from 0 to 1, and the transmon jumped back from F to ground. Okay, this is how we jump the ladder by one step. Then you can continue doing this, apply another pi GE, pi EF to go to F level, apply the next sideband, which will be detuned from the first one, and we can climb the second step, 1 to 2. F0 to E1. So that is not allowed, the F0 to E1 transition. So like under this scenario, it's not allowed. So you see that we can climb the ladder nicely, but there's problems, right? You remember the transmon had a much lower coherence, only 150 microseconds. So this mechanism will be affected by transmon decay and dephasing, and also cavity decay. Even though it has much larger long coherence time, it will still be affected by this. But the good thing is that we can actually fix these errors in real time. So let us look at just one cycle of the sideband. Okay, so pi G, EF, and one sideband, that takes us from 0 to 1. So after that, we measure the transmon. If the transmon is found to be the G state, which is normal, whatever we expected, it means that there was no error. And we simply continue with the next cycle, like going up to G2. If we find the transmon to be the F state, that means that this sideband was not done. It happens because of dephasing. So we simply apply another F0 G1 to come here. If the transmon is found in the E state, that means the transmon decayed during all this process. So we have to apply the EF again and F0 G1 again. And all this can be done in real time because this measurement is quite fast. And it actually depends on very high quality measurement or high fidelity measurement. But I'm showing you that we can have very well separated blobs, measurement blobs for the G, E, and F, so that with one shot, single shot measurement, we can detect whether it was in G, E, or F. The 3-state readout fidelity was about 98.7%, and that is super important here. And all the Purcell filter. Correct. So without param, we can achieve the same. The difference was without param, it was 2 microsecond readout. With the param, it was 1.6 microsecond readout. The fidelity was like without param was like 98, and with param was 98.7. So basically, you can fix the transmon errors in real time, and we call it sideband feed-forward protocol. So you can fix the transmon error. What about the cavity error? So cavity error simply means it will decay from it will lose single photon and decay from n to n minus 1. So in this case, 1 to 0. And for that case, we use something called a parity filter. What it means is it's like a Ramsey type of experiment. I will not explain, but what it does in the end, like we apply this sequence of pi/2, selective pi/2 pulses, wait for some time, apply a reverse pi/2 pulse, measure the transmon. If the transmon is found in the G state, that means no cavity decay happened. If it's found in the E state, that means single photon decay happened. And we can post-select on this to fix the cavity decay error. So this is just the combined picture of all this protocol. So let's see how it performs. So here I'm showing you the spectroscopic data for like preparing Fock 20. So you see when we don't apply any error correction, the fidelity, which is basically this number, is about 50%. And there's a lot of leakage in 19, 18, 17, and so on. Once we fix the transmon decay, it improved a lot. Now it's beyond 80%, but there's still significant leakage in 90. So after I applied the parity filter along with the transmon decay, it fixed both of them, mostly fixed both of them. And now this fidelity is about 95% and very small leakage to other Fock states. So this error correction helped. Here I'm showing you the fidelity as a function of photon number without error correction. So this scheme, basic scheme, the fidelity drops quite a lot. After fixing the transmon, it improved. And after fixing both the transmon and cavity decay, this is the green curve. And the fidelity here was 95%. So basically, we prepared Fock states up to 20 with more than 95% fidelity. And this is a record number until date.
So Tanay, the price you are paying is that the process becomes slower, right? You have to do it many times
exactly
to actually get there. But you know that you have gotten there.
Correct.
That's the main thing, right?
That's yeah, because we can deterministically reach there, whatever Fock number we want to go to.
Okay, so basically the better the transmon numbers are, the less number of steps you will need to do it.
Exactly. So because in that step, which means here, so if I found if the transform is very good, most of the times I will find in G, which means that all the steps are successful. So I'll keep jumping the ladder. But if it's in E and F, then I have to repeat those steps. Yeah.
So all this is for a single qubit?
Single qubit, yes.
Yeah, but you're using the same transmon for the other one as well?
Yes.
But then how do you distinguish that these pi pulses that you're applying?
Very, very
the-
good question. So far we have prepared the single qubit Fock levels individually. We haven't done it in the presence of other one, but it can be done. So as long, at least in this case, if you know what Fock state you have prepared in one mode, you can climb the ladder in the other mode because the frequency shift is deterministic and we can exactly know or measure experimentally what that shift is. So we can prepare arbitrary Fock in both levels using this key. Okay. Right. So this is about Fock state preparation. We also did entanglement between the two modes. So this state is showing a single photon excitation in the Alice mode with no photon in the Bob mode, represented as G10. And the G01 is basically single photon in the Bob mode, no photon in the Alice mode. So what we're trying to do is swap between these two states. We do that again the sideband schemes because they are connected through the transmon through this F00 level. So if we apply two on-resonance sideband drives, the photon excitation will go here and come here. That's how we can do a swap. But this is not good again because the transmon has much faster decay and will get, once you decay to E00, this process will stop and you'll get an error. To avoid that, what we do, we apply off-resonance sideband drives. So basically apply two drives which are now detuned from this F00 level. And that way you can actually avoid the transmon error. There are other errors as well. The cavity can decay again to G00 or the transmon can get excited to E10. So all these are outside your computational space and we can actually detect all of this by measuring the transmon, by like post-selecting on not E or not 00. So this is the result of coherent exchange of population as a function of time. You can see we got a very good contrast in the beginning and the contrast reduces with time. And after we post-select, the contrast increases even more. And the calculated beam split, the calculated fidelity of the swap operation is about 99.8% in this case. So what we achieved here is high fidelity swap operation. And if you stop at this point, which is halfway, you can create a Bell state, which is an fully entangled state between the two modes. However, whether we did a single photon swap, but this operation is actually known as a beam splitter operation. It's more than a swap. That actually connects higher levels between the two modes. So it can generate actually two qubit entanglement if we populate higher levels. Currently, we are actually performing experiments on that, and it will enable universal two qubit operation between two modes. Also, once we have also the single qubit operation. Yes, we can create arbitrary state between the two modes in like two qubit operation using this beam splitter operation and single qubit operation. So this is a summary of the first part of the talk. So we have this high coherence cavity with 21 and 16 millisecond lifetime. We can prepare Fock states up to 20, larger than 95% fidelity, and we can perform very high quality swap operation. So the next steps are, we haven't done the single qubit gates yet that we are working on. And again, you have to demonstrate that that beam splitter operation performs qubit entangling operation, and combine them, we'll be able to show that we have a universal two qubit processor. Okay. Any more questions?
What's the maximum D you think you can do based on the numbers?
Right. The question is, what is the maximum D we can go? So there are few limitations. So one limitation is, of course, where your dispersive approximation breaks down, which is a critical photon number. But that number is quite large in this case because we have small dispersive shift. So that number is few hundreds of photons. There are other practical limitations, like in the hardware, control hardware. So we actually had a control hardware issue because of which we could climb only up to 30. So I don't have the data here, but we climbed up to 30. We believe we can go up to kind of 100. But we have theory groups who suggest us what kind of levels would be good for computation purposes. So it turns out that if you do a power of 2, it will be much easier because many of the theories that have been developed for qubit can be translated easily on qudits. And then there are other theories who are telling that if you have 5 qubits, that is kind of sufficient to get all the advantages. So going from effective 5 qubit to effective 6 qubit is not that beneficial. So going to 32 dimension qudit will be quite sufficient to get all the advantages of a qudit.
Basically, you need 2 to the n levels to effectively have an n qubit system.
Yeah.
You have 2 sets systems, or are you including both the cavities?
No, so in one qudit, one mode, we would like to have 32. We'd like to control 32 levels. So we'll have 2 32 level qudits. So effectively, it will be a 10 qubit system. This 2 cell system.
Just in the same level.
Yes. And to control it, you just have 3 ports. That's also efficient in terms of controlling. All right. So the question is then, these are good numbers, but we don't want to stop here. How do we further improve this system? So basically what we have is this transmon coupled to 1 or more bosonic modes. So to improve the system, of course, we have to improve the individual components like the cavity and the transmon itself. So how do we improve the cavity? So remember, we mentioned that the losses are on the surface. So in this case, we have about 3 millimeter thick niobium cavity. If you zoom in on the inner surface, you'll see that on top of niobium, there is a naturally grown niobium oxide. Whenever you expose the cavity to the air, this will be grown. And the supercurrent flows in the top about 100 nanometer. So this is super important to characterize this inner surface and perform nanoengineering to improve the losses in the system. So to check that, we perform this quality factor as a function of accelerator voltage, which basically means you're putting more power in the system. And you see at a lower power, the Q drops and saturates to a certain value, in this case 3 to the power 10. This fits very well with the TLS model. So that's how we know that our loss is dominated by the 2-level systems which are lossy. Then the question is, where are the TLSs located? Well, we do have a guess, which is the surface. To verify that, we performed an experiment where we had naturally grown niobium oxide, and we artificially increased the thickness of the niobium oxide and measured the resistance, surface resistance, as a function of accelerated voltage. With higher thickness, we saw clear increase in resistance. So that tells us that the TLSs are hosted mostly in the oxide. So then the question is, how do we mitigate it? How to get rid of this niobium oxide? And actually we found a quite simple solution to it. So I'm showing you back the same plot I showed you earlier. So look at the blue triangles and squares, black squares, which are like when we make the cavities, this is the performance. So lifetime as a function of temperature, and they fit well with the TLS model. Then we bake it between 340 and 450 degrees Celsius for about 4 hours. And that improves the lifetime by a factor of 10. And so then we wanted to see what changed in this case. So we looked at time of flight SIMS data to count the niobium oxide ions, and that showed that after baking, that count drastically dropped. Or it means that the effect of the baking was that the niobium oxide, pentoxide was dissolved. Okay, that's how we got this improvement of larger than 1 second. But there's a catch. You have to still maintain the vacuum. After doing this baking, you have to maintain the vacuum, because if you introduce air, the niobium oxide will regrow and your Q will drop again. So this was very good strategy for particle accelerators because they can be kept under vacuum, but this is not really a very practical solution for making a qubit because we have to introduce this transmon. For that, we have to open up the cavity. So we wanted to look for an alternate solution. Now the question is, if I can't get rid of niobium pentoxide, why don't we make it better? So just make a better niobium oxide.
Is it actually going into the niobium, or is it evaporating?
So there are other materials studies where they looked at the depth after the So the count of oxygen as a function of depth after the baking, and this found that the oxygens actually went inside the cavity or metal.
And there it is no longer lossy.
Because the current flows in the top 100 nanometer and they have went much into, yeah. So, so we wanted to have an alternate solution. So again, this is the data of lifetime versus temperature for after baking and maintaining vacuum. So it has a lifetime larger than 1 at 30 millikelvin. Then we introduce the oxygen or air and keep it there for 15 minutes. And after that, when you measure, we see that this drastic drop about 10, a factor of 10. Then we redo we call it mid-T baking, with the temperatures we call it just mid-T baking, the temperature range of 350 to 450. Then it goes back almost to the original value. And then we have a new process. With that, when you regrow the niobium pentoxide, it dropped, but not so much. So it tells us that we should compare the red with the orange. It tells us this new way of growing the niobium oxide is much better and it can maintain higher Q even though you have exposed it to the air. So we are still working on this recipe to perfect it, like to optimize this process. But this gives us hope that this will be much practical because you can now open the cavities and easily integrate the transmon inside the cavity. So this is the way we are improving the cavity, and we believe that we should be able to go beyond 100 milliseconds in the presence of transmon with this technique. Yeah, so later it will be published, so you'll know. So this was about the cavity improvement. How do you improve the transmon itself? So for that, we do a very comprehensive study. We have many things we do. I'll go through them quickly. So we start with the substrate itself, look at how to improve the substrate, how to optimize the superconducting layer, optimize the design itself, look at the Josephson junction footprint, look at the fabrication process, and also the qubit package. So we do most of these studies for 2D chips because that's how we can get a lot of statistics. And then we also apply this for the 3D transmons. So for the substrate, we actually use our same cavities because remember cavities have a Q of 10 to larger than 10 to the 9 that enables us parts per billion precision to detect the losses. So the idea is that we first measure the empty cavity, measure its Q, then insert this chip inside the cavity, seal it and evacuate it, measure it again. In the presence of the chip, the Q will drop, and from that drop, you can back calculate what is the loss of this chip. So we tried out different substrates and figure out what is the best one. So here is the data for 3 cases. So black one is for silicon, so I'm plotting loss tangent as a function of temperature. The red one is Hemex sapphire as obtained from the vendor. And then the same sapphire, Hemex sapphire, after annealing at 1100 degrees Celsius for 3 hours. And clearly you can see that loss tangents were much lower for this annealed Hemex sapphire. So what's changed? We tried to find that. We looked at the AFM data. So this is before and after. After that, after baking, it creates atomically flat terrace surfaces, which is better. And we also looked at the bulk, and we found that there are a lot of impurities, and the concentration of the impurities dropped after the baking. And that's how these annealed Hemex sapphires are better, and we stick to that for now. I'm not sure. This is, yeah, there are a lot of materials doing the instruments. I'm not sure which instrument was. Yeah. Okay, so right here. Okay. We explored the base layer as well. So we checked what is the lifetime when we prepared the transmon with niobium, tantalum, or rhenium. These are the parameters. And again, we found that niobium more or less works pretty nicely. The maximum T1 we obtained with pure niobium devices with optimized geometry was about 0.6 millisecond. That's why we stick to niobium. And then the most important one is this niobium pentoxide, right? So I mentioned that for the cavities, niobium pentoxide is bad. And for the same reason, it's also bad for the 2D qubits as well. So you have to get rid of it. But the 2D qubits, you cannot bake because the baking was done at 400 or 450 degrees Celsius. The junction will not survive at that kind of temperature. So we had to find out another technique. and we use encapsulation. What it means is that you grow the niobium, and then without breaking vacuum, you deposit another layer of some other material, like tantalum, aluminum, titanium nitride, gold, rhenium, and so on. So we tested various encapsulation techniques and found that most of the times the encapsulation works better. And particularly the tantalum encapsulation on niobium was the best for us. So this was the first round where you can clearly see the improvement. Then we looked at how to modify the geometry. So this is kind of the standard geometry commonly used, which is the rectangular geometry. We worked with the distance and the aspect ratio and more the rounding of the edges. We call this one paddle qubit. And again, we found that the paddle qubit systematically works better compared to the other designs. And in this case, we could achieve almost about 600 microsecond T1. So again, as I mentioned, we are doing a lot of other studies, and gradually we have been improving the coherence time over time. So our average T1 is currently more than 400 microsecond. Maximum T1 is more than 600 microsecond. And the goal is to achieve more than 1 millisecond average lifetime for this transmons. So this was done for mostly 2D. As I mentioned, we applied that also on 3D. 3D usually works much better because it has much lower electric participation ratio. So we applied all these techniques like niobium encapsulation on tantalum, low loss anneal sapphire substrate, reduced junction lead footprint, reduced participation ratio, and this cavity itself is a much better enclosure. So with that, we measured T1. We found that in one case, it showed larger than 1 millisecond lifetime. However, the median value was still 500 microsecond. So that tells us that we should be able to build qubits, 3D qubits, which is larger than 1 millisecond lifetime. All right, so I'll not be able to mention other studies, but we do a lot of other studies for these qubits, like what is the effect of radiation, what is the effect of magnetic field, trenching and sidewall, growth of nanohydrides, which creates something called Q disease, creation of magnetic vortices on the cavities, studies of Josephson footprint, and so on. Basically, the idea is to look at all possible aspects of the transmon device and improve it as much as possible. Finally, so how do you plan to scale up? Sorry. So there are a few directions we are following. First, to develop a low loss quantum interconnect. So that in that case, we'll be connecting this double cell QPUs with one another. That's one way of scaling up. The other architecture we are considering is quantum random access memory architecture, where this two-cell device will be used as the computing part, or we call it manipulator cavity. And there will be a multi-cell cavity which will be acting like a memory. So and there in the middle we'll have some coupler, a parametric coupler, which will be able to swap quantum states from these cells or these modes to the manipulator mode. So the idea is that we'll swap two states from this multi-cell cavity into the double cell cavity, perform all the quantum operation, the gate operations here, and swap it back. So by doing that in pairs, we should be able to do arbitrary computation within the whole multimode cavity.
This is like the Schuster 3D quantum random access.
Yes.
Extended to the Tesla cavity.
Correct. So there they were doing only single photon, so only using it as a qubit. We want to extend it to qudits. So I actually have a very ambitious goal of building 100 qubit system, and that can look like a chandelier of cavities. And
Sorry, 100 qubit system.
Which means 50 double cell system. And we actually did the calculation. This is actually
and each qubit being at least 100 levels.
Each qubit being 32 levels, so 5 qubits. So it will be
500
qubit equivalent. All right. And this can actually fit within one Blue Force XL fridge. At least the cavities, we have to still figure out the wiring. All right, so just to summarize, the SKMS Center is trying to build a cavity qubit system using this ultra high Q superconducting radio frequency cavities, and also developing high coherence ancilla components that will enable us to build a multi-qubit quantum processing unit for computing. And the same systems or variants of that can be also used for quantum sensing and quantum simulation. So I'd like to thank all my group members for their support and help. Without I cannot do this work. And thank you for your attention. Yeah.
Yeah.
So how does error correction fit into all this?
Yeah, very good question. So we are taking two strategies. For near term, we believe that because our coherence times are so large, we don't need to perform error correction for near term applications. But then for actual practical applications, we do have to do error correction. And so we are taking help of some bosonic error correction. We are actually developing our own bosonic error correcting codes, mainly using GKP codes. So because we want to do qudit error correcting codes, so starting from qtrit, qquat, and so on. And then there are other works where we want to actually concatenate multiple codes. So GKP with LDPC codes, these are called low density parity correction codes. So that will enable to actually scale up the system to a much larger one.
Any questions? Okay. I was curious, the early work on cavity-based quantum computing used not Fock states, but coherent states to create, Schrodinger cat-like states and superpositions of that, which had some unique advantage. Of course, those techniques will even get better in your cavities because your cavities are much better than any cavities anybody is making, right? How do you compare these two approaches? I mean, are there any pros and cons of using the approach you have showed versus the Schrodinger cat state approach?
Right. So to scale up, so we wanted to utilize the fact that these cavities are much higher coherence so that we can make it a qudit system. So using Schrodinger cat, you can also make qudits, like making multi-legged cat codes. But it looks like in terms of phase space, it doesn't scale very easily. So you run out of space after going beyond maybe 4 or 8 qudit, effective qudit using the cat code. But this is a more straightforward way of achieving much larger dimension in qudits.
I see. So primarily, it's the higher dimensional is easier for you.
So these operations, like the Fock operations, are much easier for us to achieve higher dimension compared to creating cat codes.
Right. But one of the advantages of the cat codes was that, the error correction was sort of very naturally built into it, right? You have these parity errors, but you will not have that advantage, right? Your error correction will still be similar to what the qubit architecture, though I know that qudit-based error correction can sometimes be more efficient as well.
Yeah, so we are again still developing the theory for qudit error correction. So if we want to encode just with Fock levels, it will more be similar towards binomial codes. So use higher levels to effectively encode a lower number of effective logical levels. And the other direction I mentioned is the GKP code, where we think we'll be able to do maybe 4 levels for now. So 4 effective qudits.
Do you also explore losses in the junction, like subgap states, apart from this TLS picture?
So I couldn't hear.
Oh, do you also explore losses in the junction, like subgap states and other thing? That
Correct. So we have done some experiments where we tried to extract the losses in the junction. So far the idea was that we found that the losses in the surface oxide was much stronger. So we had to tackle that first. So that's why we developed all this encapsulation technique to improve the T1. So at some point, yes, the junction will start to limit us. But as of now, the junctions are not the limiting factor.
Any other questions? I have one last one about I'm guessing you're not involved too much in the cavity making itself.
Mm-hmm.
Of course, this is like decades of work. How is it actually made,
Right.
generally?
So this is the 9-cell Tesla cavity. So the ones that are built for particle accelerator actually is quite large, like 2 meter long or so. The way they are made is they start with sheet of niobium, 3 millimeter thick flat sheets. Then for this specific elliptical geometry, they make dice and then take these pieces and stamp them, and then cut out those pieces. So you end up having semicircular pieces which are elliptical in shape. Now they have to weld them together. That is the crucial part. So if you do a bad welding, there will be a lot of seam loss, which is very bad. With that, you cannot achieve Q of 10 to the power 10. So they developed this technique of electron beam welding. So they bring it under vacuum and perform welding using electron beam, which is very clean. And then they do further surface processing. After that, they achieve those kind of things. So this is done for larger size cavities. Even the, so you see the frequency is inversely proportional to the diameter. But the small ones, the 5 gigahertz, actually the double cell cavity was not made that way. It was done just through milling because it was small enough. So we started from a bulk.
Oh, through milling.
Through milling. So we made it using.
Still done in 2 halves.
Three pieces. So here. So you see this lines. So the left part was made in 1 piece from here to here. The middle part, like from here to here, was another piece. And then the right part was made to another piece. And then they are welded together. Also, okay, the beam pipes are also separated. Sorry? Yeah, 2 more pieces. Yeah, that's how they are made.
Mentioned this niobium sheet to start with. Is that also some special niobium like inside that? Or
No, this is obtained. I don't know from which vendor, but it was obtained. High purity niobium, yeah. So here, yeah, the stamping is more, the stamping is useful once you have finalized the design because you want to make it in bulk quantities. Because here we are still more in the R&D stage, wanted to just do it milling.
Okay. Any last question? All right.
I have very quick questions. It's very exciting. It seems to be forefront of what it is leveraging and things. Do you have any timelines on which you have set this goal of having these things done?
Right. So,
and how much is the gap with the rest of the field? It seems like you guys are running much faster in achieving complex qubit-based quantum computing things.
Right. So the qudit-based, not many people are actually doing qudit-based architecture. It has been like people have gained interest very recently. So in that context, we are quite ahead of it. Our goal is to go close to the 100 qubit processor in 5 years. That is our timeline. But let's see how far we can go.
Thank you very much once again. And I request everybody to join in celebrating and appreciating the wonderful lecture he gave to the ideas that we have done. And I request everybody to please come join us. We can continue the questions across the team. So please join.